Hello and welcome. Differentiation under the integral sign. I think we're probably on question 5 or something like this. Things will get a little bit harder. This is the integral in question. E to the minus 2x multiplying sine x over x integrated between 0 and infinity. Okay, as per usual, let's call this, let's say our integral, I, and let's leave a bracket, some kind of argument, because we're going to introduce some parameter quite clearly in a minute. So this is going to be our I of something. So where should the parameter be? This is a good candidate, this 2 here, which we can introduce and call it, I don't know, K. Actually, I changed my mind. You know what? Shall we perhaps... No, I will do this integral and I will do a different lecture where I'm going to just show you a general form. Let me just give you a bit of a taste of what was going through my head just now. I mean, if you look at this particular integral, let me write it again very, very quickly. I could actually do this particular integral instead with exactly the same limits, 0 to infinity. And all I need to make, in order for this to converge, all I need to make sure is A is a positive constant, B can be anything really, because if it's a plus or a minus, it doesn't really matter. If it's minus there, the signs, of course, are not function. We can pull it outside, reverse the limits, and this will still be okay. So as long as this is positive, so we got this reducing factor, this will converge. So the idea is, perhaps I was thinking of doing the integral of I of A comma B, 2 parameters within the integral, and then of course if we need our integral which is e to the minus 2x sine x, that clearly will be a is equal to 2 and b is equal to 1, but on the same by the same kind of result, I can work out perhaps the integral of e to the minus 3x sine of 2x. All I need to do is, of course, in my result, the a now will be 3 and the b will be 2. This is going to be a little bit messier. So what I'm going to do, I'm going to do this integral as I wrote it originally in there, and then I'm going to do a little lecture, not standing up on the board. I'm going to do it on my little tablet, and I'm going to show the general form for this particular integral. I'll try to remember to put a link. Okay, let's wrap this off, and we're going to do it as originally planned. And of course, I gave you a clue as to what the parameter ought to be in there. I'm gonna write it here. So I'm gonna introduce a parameter. It doesn't really matter. There I was using a and b because I had 2 things. This time let's use I of k, and it's obvious where this k is going to go. This is gonna be e to the minus kx sine of x over x dx. So it's going to be my I of k, and of course, if this is my I of k, this should be my I of 2. That's the required one that I'm trying to find. Okay, what shall I be thinking about this particular one now? Of course, if I differentiate this result now with respect to k, look at this integrand. If I differentiate the exponential with respect to k, a minus x will come to the front and will cancel this annoying x at the bottom. I'm going to get not a very pleasant integral to do, but it's definitely doable by just standard A-level methods. Okay, so let's proceed with the plan as per usual. I think we should be getting a little bit better now at all of this. So differentiating this line here, both sides, di by dk is of course d by dk of my integral, e to the minus kx sine of x over x dx. Because I have constant limits, I can swap differentiation and integration by Leibniz rule, and I don't want to waste a line in there. I have just about enough room to move that inside, so when it goes inside, strictly speaking, it should be partial, because of course the integrand is now a function of 2 variables. Okay, so we got k and x, and I'm going to do another line here purely for convenience. If you look at the integrand, this is the differential operator with respect to k. The sine x over x don't have any k dependent, so I can actually write them outside the operator. So sine of x over x and d by dk of e to the minus kx dx, and as expected, of course, this is going to give me integral not to infinity sine of x over x, and this exponential will produce, of course, a minus x, which will cancel this x here, and it will still be there. E to the minus kx dx, cancel these x's, and what else can I do in there? Maybe I can actually, you see this minus I've got in there, I'm gonna swap the limits. I don't want to put it outside because with knowing myself, I'll probably lose it at some line. I make mistakes very, very easily. So it's gonna be e to the minus kx, that's the exponential, sine x dx, just about fit it on the board. Okay, what shall I do there now? Probably, let's write the di by dk is equal to that. Let's write it on the side here, just in case, because I can actually rub it off, and we have it there for reference. So di by dk so far has turned out to be the integral infinity at the bottom, 0 on the top, e to the minus kx multiplying sine x dx. So I need to do this integral, and if you were to ask me, can you just name a couple of integrals that you absolutely detest? This particular one is one of them. I really do hate it with a passion. It's just a mess, really. So ugly, so painful to do. It doesn't matter how you do it. Of course, it can be done with standard A-level techniques, double integration by parts. Those who've done complex numbers, you can actually do it as the real part of e to the minus kx times e to the ix, and then combine and do an exponential to draw the imaginary parts. It's just a mess either way. I'm going to do it completely different today. I'm going to show a third method. This is sometimes I do it this way. I don't know why I prefer it that way. It might not actually be quicker, but I prefer it. Okay, I'm going to ignore the limit. So I'm just trying to basically do this integral. So I'm going to say, okay, to get something which looks like that, what do I need to differentiate? And quite clearly, I need to differentiate the exponential as I see it in there, and some linear combination of sines and cosines. So let's call it capital A sine of x plus capital B cos x. For the right A and B, if I differentiate that, I should get this. Okay, so I'm going to compare coefficients basically. That's what I'm going to do. Just a quick product rule now. So minus k e to the minus kx, differentiated the exponential, leaving the inner bracket as it is. So that's that bit done. And now leave the exponential alone. So that is e to the minus kx. And now we're differentiating the other part of the product. That's going to give us an a cos x minus a b sin x. And now I'm going to do a little bit of a tidy for this particular one. So what I'm going to do, factorize the exponential out, e to the minus kx, put a square bracket, collect all my sine terms. So sine terms, so it's going to be something sine x plus something cos of x. So sines is very, very ugly still, God. Minus ka, that's from this sign here, and I've got minus b from this sign there, and the cos bits minus kb, and I got cos from there plus a. Couldn't have been uglier than that. I think this is just there's a conspiracy to just annoy me, really. Okay. So if we look at what I'm trying to do, just to understand, I'm not saying do it this way, by the way. This is just something that I'm just showing. Just it's interesting to see how different people think. You can do whatever method you want. It's going to be a mess, I think. I just realized, purely because we got this parameter k, so it's going to be messy either way. But what I'm trying to do here is just differentiated. I know this should integrate to something like that, so I differentiated it, and now I'm going to compare this expression with this expression here. So if you look at what this leads to, this bit here, the minus ka minus b, that's the coefficient of the sine x, e to the minus kx, must be equal to 1. While the other coefficient, which is the causes, I have no causes e to the minus kx, this bit here must be 0. So that says basically minus kb, I'm going to move out of the way in a second, guys, minus kb plus a is equal to 0. This bit must be 0. So I've got simultaneous equations which will allow me to find the value of a and b. Probably I will rearrange this equation. So a is equal to kb, and then substitute it into the other one. So if a is equal to kb minus k, my a is of course kb, so k squared b minus a b is equal to 1. Factorize a minus b, that will give me k squared plus 1 is equal to 1. So my b is going to be equal to minus 1 over k squared plus 1. So that's my b. And my a is k times that. So my a will be minus k over k squared plus 1. So I've done the integration. So let's write a few things. Let's hope I don't rub off the things I've just done. So this is now what this thing here integrates to, where a and b are these quantities here. So I'm going to write it somewhere in the middle of the board. Let me just rub this off, because I need to still see what is a and what is b. So my di by dk, I'm moving out in 1 second, which is the integral from infinity to 0 of e to the minus kx, that's this bit here, sine of x dx, is going to be equal to limits, that's the evaluation limits from infinity to 0. That's what it integrates to, e to the minus kx, another bracket, a is minus k over k squared plus 1, lots of sine x, plus b minus 1 over k squared plus 1, lots of cos x. This actually doesn't need to be square, so let's write it to a round bracket there. And this is now the evaluation bracket. And this is from infinity to 0. Very ugly, very painful. That just really has annoyed me. I didn't really remember what the workings for this particular integral. I haven't done it for a long time, and just annoyed me just having to do this integration. Really put me in a bad mood. All right. So let's evaluate it. So what happens in there? If we put 0, what's going to happen in this line? E to the 0 is 1, so that's okay. The sign of 0 is, of course, 0, so that's gone. So the cos of 0 is 1, and therefore the only thing that will survive in there on 0 is 1 times this bit here. So it's minus 1 over k squared plus 1, minus, I'm evaluating it at infinity. I couldn't care less about the sign of the cos. If k is a positive constant, this will just die, and therefore minus 0, or this is my answer. So in fact, so what I've done so far and what I have achieved, the differential of this particular integral, which is that, is equal to, I'm going to write it on the line above now, and that's actually not a difficult integral to do, because it's instantly recognizable. So what does that integrate to? So that's the dA by, sorry, this is not my integral, this is my di by dk, is that. So if I want my I of k, which of course I of k is this, let me just write it, which of course is the integral from 0 to infinity of e to the minus kx sine x over x dx. I'm integrating this with respect to k, so that's going to be, of course, an arctan with a minus at the front. So it's minus the arctan of k plus a constant. So I need to evaluate this constant. So how I need to put a suitable value for my k and work out this quantity here. What is a suitable number for my k? So I can put k is equal to something and work this c out. We can put, I guess, 0. I'm going to write it here. If k is equal to 0 in this line here, I'm not going to write I of 0. This integral becomes e to the 0, which is 1. So I'm getting the integral from naught to infinity of sine of x over x dx is equal to minus the arctan of 0, which of course is 0, plus c. The problem that we might have is, I don't know how many of us know what this integral is equal to. It's a very famous integral, of course. It's pi over 2. It also can be done by differentiation under the integral sign, but I don't think I've actually done it. I actually tell a lie. I've done this under complex integration with residues. This turns out to be pi over 2. So if this is pi over 2, my constant quite clearly is pi over 2. But I think there's another way of doing this. If we look at this line again, can we put a different k in there? I don't like to put k is equal to infinity. It sounds a little bit odd. So that's if you put k is equal to 0. If we let k go to infinity, not equal to infinity, I'm a bit sloppy. I do apologize. I write things sometimes in a very strange way. Let's look at this line. K is infinite. If a k is infinite, careful with this different infinite, this is the limit and this is referred to, of course, to x. I'm just looking at the parameter. If k tends to infinity, all of this will go to 0. So we have basically integrating 0, which of course is 0. So if k is infinity, the integral becomes 0, but we're going to be equal to the arctan of infinity, that's this bit here, the minus, of course, I wrote it down, is of course pi over 2 and plus c. So again, the constant will turn out to be pi over 2. Okay, so it doesn't really matter. Take your pick. If you're happy to, me personally, if I was doing this, I'll probably do it with this way because, of course, it's obvious and that's a very well-known integral. If you're unhappy and you're not sure about this, treat it this way. It's also good. Okay, so we worked out the constant. So let me just clear this side and see what has happened so far. So what we've done so far, I'll write it up here and I'll move out of the way. We have come up with the answer that the I of k, which is this integral here, naught to infinity e to the minus kx sine x over x dx, turned out to be, this is pi over 2, is equal to pi over 2 minus the arctan of k. Now we're done basically. This is a little bit ugly. I hope we can see there's two different ways we can write this. Pi over 2 minus the arctan of k is just basic trig, is the arctan of 1 over k, and this is in fact the arctan of 1 over k is the same as the arccot of k. Either of these things, they're equivalent statements. Okay, so this, let's put in a box, is our result so far, and therefore we're done because, of course, what we're trying to find was this particular integral. This is our result where k is equal to 2. So we wanted, of course, to find, let me actually write the integral in full. The integral from naught to infinity of e to the minus 2x sine x over x dx. I'm not going to write, well, let's write it. Pi over 2 minus the arctan of 2, which of course is exactly the same as the arctan of a half, which, if you want to write it as an arccot, so you don't have a half, is that all of these answers are of course equivalent and exactly the same. I hope you enjoyed it. I hope you followed it. Who's laughing now?